So welcome to my presentation. It's on the photodissociation of 2,4,6-trimethyl benzoyl diphenyl phosphonate. Refer to it as that for the remainder of this presentation. So to start with, I would like to focus in on photoinitiators and kind of the reasoning behind this project. So photoinitiators are compounds that create reactive species upon exposure to light, whether that be UV or visible. There are two categories. It could be either cationic or free radical. In this study, TPOL is a free radical photoinitiator. So when it is exposed to UV light, it cleaves at this bond right here, at this phosphorus carbon bond. So photoinitiators are useful for a variety of different applications, notably in dentistry, in the adhesives industry, and in my area of interest, which is additive manufacturing, also known as 3D printing. So in this project, we're interested in seeing how the behavior of this photoinitiator would change when you vary the intensity of the light that it is exposed to. Okay. So to get into the methods that I used, we had two concepts that were modeled. So we start off with the laser intensity, which we used Rabi cycles. And so a Rabi cycle is the phenomena that is observed when you have a two-level quantum system and it has cyclic behavior in an oscillatory driving field. So basically, and I'll show this in a video later, as the Rabi cycle progresses, you have the probability density just kind of switches from ground state to excited state, which in this project there are a couple of different excited states that were explored. And then the other component was exploring the photodissociation into the two radicals, which were modeled using a wave packet method. So these are the equations that I mainly focused on. We have the main electron nuclear wave function, which you have all of the different states, 0 representing the ground state, and 1, 2, and 3 are the first 3 excited states. And then we have the partial nuclear wave functions, which are all of these right here. And then once it exhibits the pi pulse, it switches from x up to x down. And then before photoexcitation, when it's in the ground state, all of these probability densities are 0 because there's no excitation that's occurring. And so we have this equation right here. So moving on to the other important equations, we use the time-independent wave function for the probability density, which is the summation of all of the probability densities for the individual states. And so this is the probability densities broken down into their individual equations. So moving on to the results, this is the main chart of the dissociation. So basically, I changed the number of time points in the experiment, as well as the number of rabbi cycles. So we have 4 points for 100, using 1, 2, 5, and 10 rabbi cycles, 3 for 200 using 1, 2, and 5 rabbi cycles, and then 2 for 500 using 1 and 2. I use these specific numbers because after the max number of rabbi cycles, it kind of devolved into chaos in the simulation, and the results basically hit the barrier and became unusable after that. So this 10, 5, and 2 was the last number of rabbi cycles that I was able to implement before it hit that wall. And so looking at this graph, as the number of time points increases, you can see that it starts increasing in the probability of dissociation. So for 100 time points, it took all the way up to 10 before you have any noticeable amount of dissociation, versus for 200, it took 3 cycles, and in 500, it starts in the first cycle and then is complete in the second cycle. And so you can also see a sort of similar behavior in this chart, which is the chart of the bond lengths as time goes on. So you can see, again, it takes 10 cycles before you see any noticeable difference, 5 and 2. So according to these results, when you have more exposure time, and you have a higher power laser, which is modeled by the number of rabbi cycles, then you have a higher degree of dissociation in the photoinitiator molecules. So moving on, so this is kind of a preparation slide to explain the video that is in the next slide. So there's a lot going on this graph. It models the potential energy surfaces as well as the probability density distributions. So these lines, 1, 3, 5, and 7, don't change in the video as time goes on, but you can see as the number of cycles increases, the probability density distributions, so these humps right here, will change. And so we'll watch that video here. So you can see these are moving along as the excitation is occurring. The excited states are becoming populated. And that's all that I have. Questions?